We continue with this, with the layered style. We put, I discussed this in more detail because it's used a lot. And sometimes not as it is supposed to be used. This is not a layered system, so just because of these relations we said, lower level layers are not allowed to use higher level layers. So how can we model layers? Actually, we have used this type of notation where we just stack each layer, but we assume that we have actually this relation allowed to use. We can also make it more explicit. So layer and then allowed to use relation. It's possible. We can have a stack, we can have a ring like this. Here we have 3 layers, A, B and C, and B consists of sub-layers. And in this way we can also use a ring, A, B, C, and B has again 3 sub-layers. So we call it sectors. Still there's a difference between this and that. What's the difference? What is the difference? Quiz. This one is circle, that's rectangular, but
second layer is circular. B1 allowed to use B2, B2 allowed to use B3, and B3 allowed to use B1 in second.
Right. And here it's not. At least there's no neighboring relation between B1 and B3. We don't know what this means, but here there's a relation between B1 and B3. We don't know whether it's allowed to use, but this is somehow different, can have different interpretations, so be aware. There are different variations of layering. At least what's common, you have to decompose, partition in your system into several layers. Every layer should actually typically address one concern so that it becomes a cohesive set of, groups a cohesive set of modules. There's variations. One variation is the reach. We said the layers are allowed to use the layer below. Okay? But we could have also where we have somehow make this relation more flexible, the reach, where we say higher level layers can use any lower level layer. Okay. In the strict definition, it's just the closest lower layer, so the next lower layer. Okay. So if you make this relation more flexible, then we could have higher level layer can use any lower level layer. It's allowed to use. That means not through the intermediate layers, but directly. Okay. Any adjacent layer above or below. And you break the rule completely, like here. You allow also upward layers, but in the strict definition, it's not a layered style. In case you still do this, you should explicitly describe this relation. Okay, one of the issues in architecture description was that it should not be ambiguous. Okay, should not be open for multiple interpretations. Typically, if you happen to do this, then you should describe that. The case of software in a higher layer using modules in a lower layer, but not the next lower layer, is called layer bridging. Where's the layer bridging? Here. Like here, right? You just skip layer B, you directly access C. Layer bridging. If you say I want to have a strict layering, you can, no layer bridging is allowed, no upward calls are allowed. You have a strict definition of layers. Clear. There's, in practice, people just tend to be more flexible with these relations. And you could really see also upward invocations, or where they just skip some intermediate layers, so that we can have multiple layer bridgings. This is a kind of metric. If that's the case, this is typically an indication that the system is poorly structured. It's not a nice decomposition. Design decisions were not well made. With what respective? Basically portability and modifiability. So if you have multiple, many upward layers, many layer bridgings, your system will be less modifiable, less portable. But one of the key concerns, the key motivation for using layering is modifiability and portability. Okay? So you should be aware of that. So try to adhere to these relations as much as possible. Partition system into layers. Every layer should just focus on one concern. Put allowed to use relation, but don't allow to use for upward. Don't try to allow layer bridging. It's clear. This is another variation. You could have just stack them, but very often you see also some such kind of layering, where you have a sidecar, so-called a sidecar. So what does this mean if you have such a case? So in the layered view, we said we have layers plus one relation allowed to use. So what does this mean? We have a D, can mean either two, one of the two cases. And software modules in D can use software in A, B, or C, which means are allowed to use software in A, B, C, or software in A, B, or C can use software in D, or maybe both. Okay? Because we say we have 3 horizontal layers, 1 vertical layer. You can see this a lot. Not a lot, now and then you see. In this case it's ambiguous, so again usage rules must be explicitly specified. If you happen to define a layered view with a sidecar, you say, or in this case, all layers consist of 4, system consists of 4 layers. And the relation is only from left to right. Okay, possible. Or vice versa. Another variation is segmented layers, where you segment one layer. You don't put it as one complete layer, but you just provide segmentations. Typically this is the case if you have different teams in your company, in your organization, where they develop their own segments. It's possible. In this case A is allowed to use B and C. B and C are allowed to use each other, and D. Again, must be explicitly defined. Okay. You could have 3-dimensional, and this is also another variation where you put colors to make it more explicit. This is a three-dimensional case where we have these four layers. Subsystem interaction managed layer down below, and here we see a segmentation of the tools layer. Here you can do this by make it explicit to make explicit the interchangeable components, which means like they also call it like a 3D toaster. You can just get it out and put in the segments. Okay. These are the variations, layers, portability. We said, okay, one of the key issues is portability. A layer consists of modules and is accessed by some interface. To support portability, you should not expose functions that are dependent on a particular platform. These modules might be implementation units for some specific platform. Okay. By defining an interface, you already support the portability, but the next level of design decision is by constraining this interface, by not exposing functions that are dependent on a particular platform. So the interface is more general, with what in mind that perhaps later on we might need to change to a different platform, where so you could have here like get call, set call, whatever, some operations, but should not be specific to platform, but more platform independent. If you can ensure that, your system will be more reusable and more portable. Okay? Because the same interface will just apply. Okay, this could be a question for the quiz. He said, okay, layered style is typically is a style from a module view type. So it visualizes the implementation units, the structure of implementation units by layering actually, by partitioning the system into layers based on allowed to use relation. Could we divide the layers of an existing system by analyzing source code? So imagine you have a system. It doesn't have an architecture. You have to define an architecture for it, and you analyze the source code. Based on the source code, you want to actually define the layers. Is this possible? By just analyzing the source code, defining the layers.
It's possible we can look at the source code and if we...
It is possible or not possible?
Possible.
Possible.
If we see interface of source code and where we use this interface in source code, we can layer.
So then you will define the layers. So you say it's possible because then I will analyze the source code, look at which modules use which module. Based on that, I group these modules. So what do you think, Meli? Would we have to write layers?
Yes. I think it's possible, but very hard to analyzing source code.
It is hard to analyze source code, but imagine we have to write tools. Would we have to write layers then?
It's possible.
Okay. Yes, so but somehow you have to. The idea is that you have to design an architecture, but first, but sometimes you don't have. So, but this is just a question to. You have. Can you define? Can you indicate the layers based on by looking at the source code?
As well as I know, we have automated tools which returns source code to the class diagrams, module diagrams. With that module diagrams, we can see which module or class interacting with which one, and we can see if it exists a layer. We can easily see the layers.
Okay.
We cannot do it just by looking source code, because even the related modules can call each other in the same layer. We should have some constraints in order to say that, I think. And due to the flexibility, maybe the lower module can call the upper level module, and we cannot know that without specifications.
Mm-hmm.
It's,
So you say it's not possible. Actually,
without some
right.
constraints and specifications.
Actually, that's the right answer. We can look at the source code and try to find the use relation. It's possible. There are nice tools for that. But if we say it's allowed to use, not use relation, right? It's a potential to use relation. What happens to the modules which do not use in the program, but which are allowed to use? Okay. If you would just structure your system based on the use relation, you would not have actually not the right layers. Okay. If you are lucky, the use relation will reflect the allowed to use. But allowed to use means more than just the actual case. Okay, it's clear. So it's partially true. Excuse me.
With intuition, we can know the layers. We can define the layers. By experience or something like that.
Yeah. Then you use other approaches. With intuition, by experience, and you look at the allowed to use. That's true. But if you stick to just analyzing the use relation, automatically, then you will not end up with the right set of layers.
The answer of this question may be both yes and no.
Yeah, it's partially true. Partially true. Partially true, but no. The source code may disclose what uses what uses what, but the relation is allowed to use. But it's partially true. Why? If it happens that the use relations are also the allowed to use. Okay. We have seen this before. Confusions, calls versus use. Use relation is not a calls relation. Like a program P1 can use program P2 without calling it. And like here, so here P0 calls and uses it. P1 is upward call. It's not use relation, but it's just notify, error notification. For example, this exception handler, but it doesn't use. Layers are not tiers. Okay. What are tiers? Tiers represent the locality of processing, hardware nodes, machines on which the software runs. Layers are a cohesive set of implementation modules for which a common interface is provided. Tiers, typically hardware, layers, software. Layers might, however, be mapped to tiers. Okay. You could have presentation layer, business logic data server. You could map this to 3 different machines, but could also on one machine. If you map to 3 different machines, you have 3 tiers. One machine, one tier. Okay. Typically, tiers pop up in the deployment view, where we map the software to hardware nodes, where we define what the client is, where the service, whether we have middleware, and how we allocate software, how we allocate these layers, these modules, to these hardware nodes, to these tiers. Okay? Layer is not a tier. How do you model layers in UML? we have seen that we could stack them in the informal notation. In UML actually has no built-in primitive corresponding to a layer. You can, however, represent like packages, stereotype packages. What's a stereotype here? Layer. We have seen that we could use also stereotype to describe architecture. Okay. And the same for allowed to use. So our layer could be represented as a set of packages. Because a package is quite suitable for this purpose. A layer is a grouping mechanism, package also. So we have seen actually the module view type. We have seen the predefined styles, the composition, uses, generalization, layered. Typically, where can we use the module view type for construction? Module view type. The module views provide a blueprint for the source code. It defines the implementation units. Typically, you need to implement these modules, these classes. It provides it's a means for analysis. Modules implement functional requirements of the system. You can use this module view for traceability and impact analysis. If you are in case of changing requirements. For communication, you can use to explain the functionality of the system. And of course, education of new developers. What the module view type is not for. Module view types do not represent the structure between runtime entities, and as such they are less useful for runtime behavior analysis, for example for performance analysis. If you want to do a good performance analysis, typically you need architectural views which represents these runtime elements and their relations. What's the relation to other view types? We will see that we will have component connector view type, allocation view type. The elements in the module view type typically are mapped to views in the component and connector view type. Okay. Classes will be mapped to components, for example. Implementation units in module views have a mapping to components that executes at runtimes. Sometimes it's quite simple, it's one-to-one mapping, but can also be more complicated. We have many-to-many relation. Summary here. So we have decomposition style, shows how responsibilities are allocated across modules, especially suitable to show newcomers and for performance change impact analysis. User style shows how modules depend on one another. It helps to achieve incremental development and the building of useful subsets of the system. Generalization style relates modules by showing how one is a generalization or specialization of the other. It's widely used in object-oriented systems, shows inheritance, and is used to exploit commonality among modules. Layer style divides the system into a set of virtual machines related by allowed to use relation. Helps to achieve portability and modifiability. Okay. Questions about module view type so far? These are the predefined styles. In principle, you can define also new styles. Okay, new module view, new styles based on the module view type. Okay, then we continue with the second view type, the component and connector view type. It documents the system's units of execution. It looks at the system from the runtime perspective. The system is running and typically visualizes what the elements are, the units of the execution are. So typically the elements are component and connector, therefore it's called component and connector view type. Relations is an attachment relation. Excuse me. Component. Definition is principal processing unit of executing system. Example of components, objects, processes, or collection of objects, etc. So any unit which has some runtime behavior. Connector is the interaction mechanism for the components. It could be pipes, repositories, sockets, or even middleware. Relations is attachment. So, while we have components, parts. Ports are associated with specific connector roles. This is an example of the component diagram as a component view. Where we have 3, 6, 8 components, where every component has some provides requires interface. That's the issue here. A software component is a unit of composition. We have discussed this before when discussing architectural description languages. Software component is a unit of composition with contractually specified interface and explicit context dependencies. A component has a provides interface and a requires interface. Provides interface defines the services, the operations that are defined by the component to other components. Requires interface defines the service that specifies what service must be made available for the component to execute as specified. We have seen this, that's a component meta model. Component consists of interface. Interface can be a required interface or provides interface. Interface typically consists of a set of operations, and operations can have parameters. You can elaborate on this, but this is the general view. Okay. Component is a unit of execution with provides requires interface. And we typically decompose these components to make a running system, where we typically have also to write some glue code, but that's the case. So how do you model components in UML? There are alternatives for components. The order, either you could have use a stereotype, or like this, or stereotype and a symbol. Alternatives for interface, either textually, where you provide stereotype, provide interface, required interface, or visually, where you have a lollipop for provides interface and the socket for required interface. So you have separate components, individually deployable. You can compose these by typically connecting these provides and requires interfaces. Every component has also a port. It's a named interface which defines a set of operations and events that are provided and that are required. So this is like a port which has here, in this case, a provides interface, requires interface. Okay? Well, where's the place of a component diagram typically? Imagine we could have a layered system. System is decomposed into layers, and in this case it's represented as packages, package diagrams. Layer consists itself of submodules, and every module, every package, submodule, subpackage can be implemented as a component diagram. So here's the component. This represents the runtime entity. The component themselves, this is one component, can be implemented as a set of, for example, classes. Okay? So we said components as a higher level of abstraction than objects. Okay? So that's the relation. You can take, of course, one class can appear in different components. What did we say? So the elements in the module view are mapped to elements in component connector view. This relation can be one-to-one, where we typically map each class to a component, but could also be many-to-many. So that means that every class can be mapped to several components. Okay. Or that's one possible. And then we have one-to-many. If you look at the book on the views and beyond approach, they have also defined 2, 4, 6 predefined styles of the component and connector view type. Pipe and filter, shared data, publish, subscribe, client server, peer-to-peer, communicating processes. In each of these styles, the elements represent units of execution, and the relations are also runtime relations which relate to runtime behavior. We have the similar situation. At the top we have the view type, component connector view type. The view type is constrained. Typically results in a set of styles, and by instantiating from the styles we can derive the views, contextual views. The CNC pipe and filter style, this is an example. I will not discuss all of them, just a few. Here the components are filters. Filters are runtime entities, which are data transformers that read streams of data from input ports and write streams of data to output ports. The connector types are pipes. They convey streams of data from one filter to another. Here are the filters. This is an example pipe and filter view based on the style. This is the filter. It gets lots of data. It processes data. It puts it to the output. And the arrows here means the views. The relations are attachments. Attachment relation associate filter output ports with data in rows of a pipe and filter. We said so we can connect these components together. Here the components are the filters. The filters are connected through these pipes. Topology pipes connect filter output ports to filter input ports. This is another style, the shared data style. Component type here is a shared data repository. Connector type are data reading and writing. Here, these are the components here. We have a repository. The relations are again attachment, which relation determines which data accessors are connected to which data repositories. Here we have the two gateways, data accessors, runtime units of execution, which access the repository. Okay. The relation here typically is SQL relation. RPC, remote procedure call. There's some maintenance tool which accesses the database, the repository, through a remote procedure call, which means that it's located on a different machine. Again, this is one example of a style. This is the CNC communicating processes style, where you focus on runtime view. Your elements here are processes. The component types are concurrent units such as tasks, processes, and threads. The connector types, data exchange, message passing, synchronization, control, and other types of communication. Attachment relation as defined in the CNC view type. So typically we get, so this is one example of the communicating processes view. An architecture view consisting of set of processes. Here they have also a repository. The relations are RPC and message calls. Okay. So this is not from the implementation unit, but when the system is running, we will have this view. What the CNC view type is for is used to reason about runtime system qualities. This was not possible in the module view type because it focuses on implementation units, more design perspective. This is more runtime system, so as such you can use this for performance, reliability, and availability analysis. This is not appropriate for representing design elements that do not have a runtime presence. Shall we break or? Okay, we continue with this. Allocation view type, that's the third one, the view type. Here you focus on, you have a software you have to map to non-software. Sorry. The allocation view types presents this mapping of the software onto its environment. The elements are software elements, typically from the module view type and the component connector view type. Relations is allocated to. So this view type presents a mapping from this from the module and component connector view type onto environment. What's the environment? There are three different kinds of environments here. The hardware elements, that is how do you allocate your software to hardware. The file management structure, how do you map your software to your files and directories. And the third one is organization teams. How do you map organization, your software to your team. Based on that, they have defined three predefined styles. The deployment style, where you describe the mapping of components and connectors onto the hardware on which the software executes. Implementation style describes mapping of modules to the file system. And work assignment describes mapping of modules onto the people. See? So allocation is not just the deployment, but here we have three different styles. Again, the picture is similar. At the top we have the allocation view type, we have the styles, which define the constraints, the relations, and if we instantiate, we get the views. Allocation view type, the first view, deployment style, which maps software to hardware units. Usually elements from CNC view type. The environmental element, they are computing hardware, processor, memory, disk, network, and so on. Okay. Relations allocate to or migrates to if the allocation is dynamic. That means if you can, at runtime, allocate software to different machines. It's possible. Topology unrestricted. Allocate the relation either static or dynamic. This is an example where you have typical the machines, the environment, and where you define the software elements. Okay. So it represents both the hardware elements plus the software that you map on these hardware elements. If we have such a case, then we have typically deployment view. This is a deployment view. If we use UML, in UML we use the cube notation for representing machines, hardware elements. Like here, this represents the client server. Server is the host machine. This is one computer. This is a client machine. And here we see the mapping of software components on the hardware. At the client machine we have just one component, planner. At the server we have scheduler component and one repository. Okay? So mapping of software to hardware. There's the implementation style defines the mapping, not software to hardware, but to your file management structure. In the end, you have to implement the architecture. Okay? You have to do the detailed design, but also the coding. Typically, this defines how you structure your system in your file directory. Software elements are the modules. Environmental element is a configuration item such as file or directory. This is an example of implementation view. The relations here is again allocated to and containment. In this case here, for example, this symbol shows the folder with the name of the module. So we take one architectural module, like here A, and we define how it is structured over the folders and over the directories. Here we have the a.csc related to this module, a.h, this documentation file and configuration. Okay. This again is this is the allocation style. It's implementation style from the allocation view type. Okay. The third type is the the third style in the allocation view type is the work assignment style. Here you don't map to hardware or whatever, but you map to persons. Environmental elements are organizational units, such as person, a team, a department, a subcontractor, and so on. Relations allocated to, like here, these are our elements, the subsystems, and in this table it is described how you map these software to non-software units, in this case organizational units. For example, the data processing team is allocated to data team, a team consisting of set of persons. What does it mean here? So typically they will describe how the system should be implemented. Okay? Now at this time, is this clear so far? Yes? Okay, then, so this views and beyond approach is quite recent. We have also seen the different views in UML: design view, process view, implementation view, deployment view. How can we relate the views in UML to the views in views and beyond approach? We had 4 views, right? 4 plus 1. The design view, process view, implementation view, deployment view. Here we have 3 view types, but having different styles. So any ideas? Any ideas about this? So what's the design view? Why would you typically put this? The design view of UML as well. Which view type does it belong? Module view type. Why?
It contains design elements, not runtime.
It's not. It's design perspective, not runtime. And typically, what kind of style? More hybrid style, right? In design view they use inheritance association part of, so we could say it's like a style in the module view type where you define where you have a combined view actually, where you allow all these relations. The process view, which style? CNC CPU type, of course, right? It's a runtime. It's typically this, right? Communicating processes. Implementation view. It's also somewhere here, CNC. Deployment view. Deployment view. Allocation and deployment style. You see, but in the allocation view type we have 3 styles. Where's the work assignment style in UML? You have it?
Maybe implementation.
We don't have it. There are 4+1 views. Okay? So in that sense this is more general, it's broader. If you would sum all these styles, 4 in the module, 6 or 7 in CNC, and 3, it's about 13, 14 styles. Plus you can define your own style. So the idea is that you have multiple views. So architecture should have multiple views, but it's typically not restricted to only views only. You could have multiple. And that was also the idea here. They categorize all these views. It's a broad category. But it's also the idea is that you can define your own styles where necessary. Okay. Okay, let's break.